video. All right. And we have this. That's 2. Yes. All right. We need attendance. Okay. Oh. There we go. Okay. All right. I opened up attendance for y'all. If y'all want to go ahead and do that. We got 3 minutes. Oh, I want to set up mine. I do want to say y'all have been really awesome about wiping everything down, not leaving the wipes laying around. Y'all have been really, really awesome. So thank you. And everybody's been wearing masks. Awesome. So I guess to start today, I have 2 jokes for you. I have one Charles joke, and then I have one that I actually have for y'all. All right, so what do you get when you cross a penguin and a jalapeno? A chili pepper. Okay, that's Charles's joke. That was Charles's joke. Here's yours. And I actually had to write this one down. Where do you take someone who has been injured in a peekaboo accident? The ICU. That was actually almost on his level too, but I wanted some kind of a medical one for y'all. I thought that was pretty good. All right, so you should have checked in on attendance. If you have not checked in on attendance, please go ahead and do that. I hope y'all are enjoying these jokes. If not, you're just going to be tortured for the rest of the semester. Okay. So for Thursday, we're gonna do our regular. We're gonna finish the in-class problems that we normally do, but you're gonna need one more thing for Thursday. So if you go to Moodle and you go to chapter 6, right under, why it does that with that statement, that red statement, I hate that it does that. But here, you see lecture slides, in-class problems, and then you see chapter 6 activities, glycosidic bonds and reducing sugars. Those are just PDFs that you either need to download or print out for class. So you're not going to turn it in, but you're going to work on it. So whatever works best for you, and I don't know why it's not loading, but it should load. I'll double check it, but if you can't get in, send me an email, but it should work. I don't know if it's the internet or what right now, but anyway, that's where it is, chapter 6, and then right under the in-class problem. Okay, so we close that, and we need to do some quick questions. All right. Here we go. So find the correct match between the term and the description. So each one starts with a term and then has a description. I'll give you a minute and a half. Okay, 5 seconds. Click in something. Okay, so in order to answer this one, you had to remember what's the difference between poly, di, oligo, and mono. So tell me, what is polysaccharide? 10 or greater glucose units or saccharose units. Disaccharide, 2, oligo, 3 to 10, mono, 1. So a polysaccharide cannot be hydrolyzed into simpler forms. You have 10 units. You could chop off each and every one of them. So is that one right? No, that's not a good match. Disaccharide reacts with water to produce 2 monosaccharides. Yes, that's 2 rings being chopped in half, and now you get 1 ring each. So a disaccharide into 2 monosaccharides. That's good. Oligo reacts with water to produce 2 monosaccharides. If it reacted with water, you would get like 1 monosaccharide and 1 disaccharide if it were 3, right? So that one's not it. Monosaccharide reacts with water to produce a few monosaccharides. You only have 1 to start with. So you can't make any, you can't produce any, right? So that's not it. So it should have been B. Good. Okay. Identify the highlighted functional group. Identify the highlighted functional group. So this is a good reminder that if you have those flashcards made for those functional groups, you should keep studying them because we're going to keep using those functional groups from now until almost the end of the year, end of the semester. Ten seconds. Okay. So the general format for our functional group, right, is you look at what's highlighted, and then what do you do with the rest of the molecule? What do we represent that as? An R. So what functional group has that configuration? Y'all should have said that it is an aldehyde. How do we remember an aldehyde? There's only one functional group. There's only one R group attached to the functional group. And so that's all alone. So it's aldehyde. Okay. How about this highlighted functional group? Okay, 10 seconds. Okay, if we have a carbonyl group right here, and it has one R group here and one R group here, what do we call it? What y'all say? A ketone. A ketone, good. One of those you just got to remember. All right, one more functional group. What is this highlighted functional group? Last functional group. Ten seconds. Okay. So, what did we say? Oh, good. So the majority of y'all said that it is a secondary alcohol, but I saw a lot of people thought carboxylic acid. How is that alcohol different than a carboxylic acid? The carboxylic acid would have to be an OH here. It would have to be attached to the carbonyl group. That would be a carboxylic acid. But in this case, our alcohol is bonded to our carbon here. So because it's attached to something that's not a carbonyl, right? Then what we need to do is count how many things are attached to the carbon that has the hydroxyl group. So that's 1, this is 2. So this makes it a secondary alcohol. If this H were something else, then it would be a tertiary alcohol. But because it's just a hydrogen, we don't count it, right? So we only count the R group. So it should have been a tertiary alcohol. All right, I think I got 2 more, 1 more. All right, what are enantiomers? What are enantiomers? I know. 2 more, this one and 1 more. Ten seconds. All right. So what are enantiomers? Look at A. Different molecules that are non-superimposable images. True or false? True. That's true. Okay. D and L glyceraldehyde. That's true. What's the difference? If I were going to draw, right? There's a carbon and it's got a double bond on it, right? And here's the same thing, it's a carbon with a double bond. How do I differentiate between D and L? Right, this is a CH2OH. How do I know the difference between the two? Left and right. What's on the left and right? We're looking for the hydroxyl group, right? That's farthest from the carbonyl. So we're going to go carbonyl and we're going to go farthest from it. Oh, I went too far because I wasn't watching where I was going. So right there. So do I put, for a D, do I put it on the left or the right? On the right. Now for the enantiomer, what do I do with it? I just swap it. So it's going to be on the left. This is going to be on the right. So that's how I know my D and L isomers, right? So that is true. Those are enantiomers because they are non-superimposable mirror images. How about cis and trans? If I had something that is cis and trans, what we've been talking about so far are carbon-carbon double bonds, right? And so if I had this configuration, what would I be? I heard it. Cis, you would be cis, good. Here, I would be trans, right? Are these mirror images of one another? If you put a mirror between them, would it be a mirror image? It would not be. So cis and trans are not mirror images. So it can't be all of the above, so then it must be A and B. So what did we say? D. So a lot of people wanted to say A, so that's good. That's good, but be careful with this cis and trans. Okay, is that my last one? No, one more, last one. All right. How many chiral centers are present in this molecule? Remember, you got a minute and a half. Ten seconds. Okay. So what do we have? How many chiral centers? Y'all should have said that there are 3 chiral centers. Where are my 3 chiral centers? 1, 2, 3. This is a Fisher projection. So how is it super easy to find chiral centers? Anything that is a perfect plus, right? So these are all chiral centers. How about right here? Is this a chiral center? Why not? It's a double bond, so we don't have 4 different things attached to it. And we know that these carbons are not chiral because they're drawn out. They're not listed, but they're not chiral really because they have 2 hydrogens attached to them. Okay, so you should have said 3 carbons. All right, so that is it for clicker. We're going to move on to our in-class problems. Okay, and this way. All right. So the first thing that we have to do is to talk about reactions that monosaccharides can undergo. So monosaccharides, in order to understand their reactions, we have to understand how we draw them. So part of that is understanding how the functional groups attached to the ring are oriented. So remember we talked about trans and cis, right? So if you are trans, are you on the same side or different, the 2 groups? You're on different. And if you're cis, you're on the same side. So now when we talk about sides, what we're talking about is the ring. So if you took that ring and you set it on your desk so that the ring would lay flat, then we would look at groups that would come up from the ring and groups that would go down from the ring. So that CH2OH, this is going up. So this would be on the top of the ring, be sitting up. This OH here on the side would also be up. So is this a cis or trans configuration? It's cis, it's the same. But when we talk about sugars, we're not going to call it cis anymore. We're going to call it beta, the beta anomer. All right, so let's go try. You're always going to compare the hydroxyl that's on your anomeric carbon. How do I know what my anomeric carbon is, by the way? How do I know that this right here is my anomeric carbon? It's bound to what? 2 oxygens. Here's one, and then here's the other. And one of those oxygens is going to be in the sugar ring. Okay? So let's go try some new ones. Here we go. All right, take a look at the molecule in A. Is it alpha, the alpha or the beta anomer? So if we look, we find our anomeric carbon, we find the hydroxyl attached to it, we find the carbon that's sitting on top of the ring, and we compare them. Are they the same side or different? They're on the same side, and so normally we would call that cis, but we're not going to call it cis anymore, we're going to call it beta. So the way that I remember this is the alphabet, right? A, B, C, A, B, what, like goodness today, A, B, C, D, right? So beta and cis go together. You gotta have some way to remember it. If that doesn't work for you, you can make up some little story, whatever it is, but make something work for you. All right, the next one, are we alpha or beta? We look at our anomeric carbon, we find our hydroxyl, we find our carbon above the ring. We're going to see that they are different on different sides of the ring, and we know different is trans, and another way to say trans is alpha. Questions? All right. Make sure you know how to find your anomeric carbon. It's going to be so important. So important. Okay. Now, here comes a little bit harder. We know what alpha and beta are, but now we have to convert from this straight chain Fisher projection into how these molecules actually exist. And so they exist as rings. If we're going to exist as ring, that means we have a chain and the two ends are going to hook together. What atoms are going to participate in that new bond that hooks the ends together? Let's number our carbons. Carbon 1, 2, 3, 4, 5, 6. You're always going to number your carbons like this in a Fisher projection. What if, for example, you had something like this? This is just a pretend molecule I'm making. Where's carbon 1? Is it the one that participates in the double bond? No. Which one is it? It's the top one. So the one that's participating in this new reaction, see, this carbon is going to bond with the oxygen in the hydroxyl farthest away. So is it always going to be carbon 1? No. You need to be careful. If it's an aldehyde, it will be carbon 1. What is this that I just drew? This is my pretend thing. What did I just draw? An aldehyde? No, what did I draw? A ketone. I always want to put a Y on it, but it's not. All right. So can I erase my pretend diagram, my pretend drawing? Yeah? Okay. So just be careful with that numbering. All right, so draw the alpha and beta anomer of D-aldose. Okay, so what I'm going to do is I'm going to draw, why am I doing that? Come on. I'm going to draw a ring. My ring is going to have how many carbons in it? Okay, I hear 5 and 6. How many carbons are in the molecule? 6. But how many carbons are in the ring? Only 5, because here's 1, there's carbon 1. Now we're going to have carbon what? 2, right? This one is not in the ring. It sits on top of the ring. Okay? So be careful with that. All right. So I always like to start drawing with my oxygen in my ring. And then I know I'm going to have a 5 carbon ring. So it looks like the structure for a 6-carbon ring, but what's the 6th atom in the ring? Oxygen. We just don't name it. We just don't name it. All right, so my anomeric carbon is my carbon 1. So I want to draw the alpha and the beta anomer. I'm going to draw alpha first. So I put in almost all my carbons. Where do I need to put in my next carbon? On top. So coming off of carbon 5 is carbon 6. So that's CH2OH. Now, if I want to draw the alpha anomer, my hydroxyl needs to go up or down. It needs to go down because alpha is trans. So my hydroxyl is going to go down. What do you have to put on the other side? Hydrogen. Now, when you look at a Fisher projection, if we look at the groups that are here on the left, are they going to go on the top of the molecule or on the bottom of the molecule? They're going to go on the top. The ones here that are on the right are going to go on the bottom. Unless you're making an alpha and beta anomer, right? And then you have to put it in the right place for this last one right here. But we've already done that one. So now fill in the rest. How about carbon 2? Does the OH go on top or bottom? Carbon 2, here's my carbon 2. Does my OH go on top or bottom? Top. So then it'd be H going down. How about carbon 3? Does my OH go on top or bottom? Bottom. Okay. Then carbon 4, top or bottom? Bottom. I'm drawing it on the top. Bottom. All right. And then carbon 5, right? What do we have to do with carbon 5? We've got that oxygen already in the ring. So now we just need to add a hydrogen in. So I'm going to kind of erase my numbers on the inside. I feel like it's gotten so clustered. Okay. So what you should have is an OH here, H, H, and then coming down is an H. If I were to draw my beta anomer, what's different? It's got to be the same ring. Everything's going to be the same except what? Except the OH on the first carbon, but really it's the anomeric carbon, right? So that would be H. Yes, thank you, Hayden, for participating. Awesome. So the only thing that's different is right here versus right here. So, oh, I didn't label it. What do we call this one? Beta. Oh, and I heard on the homework, you had to write D and L on the, when you were naming the different sugars, you have to do D and L. It does not automatically assume that it's D. All right. Okay, so we good on this one? Can I change screen? Yes, all right. Okay, so before, can I move this? Oh, I can. Okay, before we do the problems from the next little part, right? I think it's really important that we stop for just a second and talk about what can happen when you have a sugar that has an aldehyde in it. So remember your basic structure for your aldehyde? carbon, and it's only got one R group, so it's alone, but then it's got that carbonyl group and a hydrogen. So when something undergoes oxidation, tell me, if I want to make myself a little cheat sheet, here's my little cheat sheet. If something undergoes oxidation, how are the different ways that that could happen? There are 3 different things that could happen. You could add an oxygen or gain. What else? You could lose hydrogen. And then you got to remember the oil rig, right? OIL means oxidation is loss of what? Electrons. That's oxidation. How about reduction? You could lose oxygen. What do you gain? Hydrogen. And then this is the rig, R-I-G. So reduction is gain of what? Electrons. My strong suggestion to you is when you get your exam, right? You've done your setup, you've viewed the area, you've shown the camera that you have a blank sheet of loose leaf. Did my camera? Oh, I tapped it and went out, didn't it? Oh, no, I think it died. Maybe. Can you hear me now? Yeah. Okay. All right. So when you get your orientation done, your surroundings done, you have that sheet of paper and you show it to the webcam front and back, put that paper down and go to town on it. Write down what you know. Like this right here, that's what I'm going to call it the cheat sheet. What should you put on a cheat sheet? It's not really a cheat sheet, right? But this is what you should put as soon as you can write on your loose leaf sheet of paper. This is, you need this. And you do not want to be in the middle of the exam going, oh my God, is it gain or loss of electrons? Is it adding or losing a hydrogen or not? Oh, I'm so confused, right? But what if you got your paper, you knew what it was, and you wrote it down? How much more confident would you be through the rest of your exam? A whole lot more, okay? So from here on out, I'm gonna say you should add this to your cheat sheet. You should add this to your cheat sheet. That's what I mean, okay? I'm trying to give you pointers. All right, so back to this. We have an aldehyde. It is gonna undergo oxidation. Tell me what happens in oxidation. One of these 3 things, right? We're either gonna add an oxygen, we're gonna lose a hydrogen, or we're gonna lose electrons. How do we know if it's adding or losing oxygens and hydrogens, or if we're talking about electrons? What's the difference? When we talk about adding and losing electrons, we're talking in general about metals and nonmetals, but we're not talking about carbon. We're not talking about organic compounds. When we talk about organic, so carbons and hydrogens, we're going to talk about adding oxygens and adding hydrogens in oxidation reduction, okay? So do we have a carbon, do we have an organic compound in an aldehyde? Good morning, good afternoon. What is it after? It's afternoon. We have an organic molecule because we have an oxygen bound to a carbon. That's right. Okay, so Hayden's saving y'all on the chat. So we're going to actually add oxygen here. So if we add oxygen, what's going to happen? We're going to go from having just a hydrogen here to now having an OH. What happens when I have an OH bound to a carbon with another oxygen? That's now from the clicker questions, remember? A carboxylic acid, right? When you have that carbonyl and you have the alcohol bound to a carbonyl, that's a carboxylic acid. Do you need to study the side groups, the functional groups? Absolutely. All right, now, and if we go in the opposite direction, if we go in reduction, if you have reduction, what are you adding? Hydrogens, you're adding hydrogens. So when we do this, if we look here at our carbon before only had one hydrogen attached to it. We add another hydrogen and we're going to add a hydrogen to our oxygen. So what do we get? A plain old alcohol. This is why it's really important to know the difference between an alcohol and a carboxylic acid, because they're very different things. Okay, they're going to behave very, very differently. So you might want to put that on your cheat sheet. Okay, everybody got that? You okay? A little worried about y'all. Y'all are quiet today. I'm not used to it. All right, so let's go try some problems. All right, we have a sugar alcohol erythritol. It's often included in low-calorie sweeteners. It is 70% as sweet as table sugar. Erythritol is the reduced form of aldotetrose erythrose. Now say that 6 times fast. Draw erythritol. So what are we going to do here? What kind of a reaction is happening? A what? A reduction. A reduction. What kind of a functional group do we have here? What do we have? An aldehyde. An aldehyde. So if we have an aldehyde and it undergoes reduction, what happens? We add hydrogens, and we're actually going to add H2 because we have 2. That's right. Hayden's just ahead of the game. All right, so what happens when we do that? We end up with carbon, right? We keep our main structure, but instead of having a double bond here, what are we going to do if we end up adding a hydrogen here and adding a hydrogen here? What are we going to end up with? It's going to be an alcohol. And then you need to put that extra hydrogen. And now we can draw the rest of the molecule exactly like it was. And you can pretend like that's a straight line. So do you see how the stuff in red is the only new stuff? And now we have an alcohol. But I'm going to warn you, that's not the way that they show it. So how could we show the same molecule? I'll put my carbon in. OH, H, OH, H. But show it in a more condensed form. CH2OH. Do you see how these two are equal to one another? It's just 2 different ways of writing exactly the same molecule. Now, if you were drawing for me, you could draw either one and I would give you credit for it. But because it is a multiple choice exam on the computer, right, you have to be able to select the correct answer as it's drawn either way. So I'm trying to point these things out to you in class so you don't get caught on them on the exam, okay? All right. Okay, so now we've gone from monosaccharides. Now we're going to talk about disaccharides. We're going to talk about their reactions and then common disaccharides. So identify the following reactions as condensation or hydrolysis. I want to come down here, and this is something I want you to add to your cheat sheet. The question was, is it condensation or hydrolysis? Tell me about condensation. In condensation, you make water. That's true. So water is a product. That's true. What do you start with? Two molecules. You do start with two molecules. Each of those molecules is going to have an alcohol. Okay, so we'll call it R1 and R2. Make it easy. So where does that water come from? We're going to take a hydroxyl group from one and a hydrogen from the other. Does it matter which one? Absolutely not. Does not matter which one. So you end up with HOH, right? And what is HOH? Water. It's the same thing. Now, what are you left with in blue? Your first R group. Now, what's going to happen is when that water is formed, the bond is going to be formed between one group in the first molecule and the oxygen in the other molecule. So just pick up the blue where we left off. We did R1, skip ahead to oxygen, and then R2. You should have this on your cheat sheet. Okay, now, how is condensation different? And I'm going to erase this just so I can put them in right under one another. How is hydrolysis different than condensation? It uses the water to break a larger molecule. Okay. So how does that work? If we have H2O, we have HOH, right? So I can break the bond and I can take a hydrogen and attach it to the oxygen. And then I can take the hydroxyl and attach it to the R group. And it doesn't matter which one you do which. You just have to put a hydrogen with the oxygen and put a hydroxyl on the other side. Okay? So then what do you end up with? You end up with R, O, and then we have a hydrogen bound to it, plus we have our, well, OH, but I want to put my hydrogen first. And that is bound to R2. So do you see how we used up a water molecule? We did the opposite. R1. Hydrolysis and condensations are the reverse reactions of one another? Yeah. You need to be able to recognize these. And if I show you a reaction, you need to be able to tell me if it's hydrolysis, tell me if it's condensation. You need to be able to predict the products, right? All that kind of stuff. So these are really good for a cheat sheet, but don't really cheat, please. All right, so identify the following reactions as condensation or hydrolysis. A disaccharide breaking into two monosaccharides. Yeah, Jason, so the question is, if you're writing this out, can you use the reverse arrows for the equation? You sure could. You could take one of these and you could say, okay, going this way is condensation. And you could say going this way is hydrolysis. Yeah, if you want to save space and stuff on your scratch paper, you can do that. Absolutely. All right. So a disaccharide breaking into two monosaccharides. If we have one big molecule going into two smaller, what kind of a reaction is that? Hydrolysis. A reaction in which two molecules combine, forming one, and a molecule of water is produced. Condensation. The breaking of a glycosidic bond. What is a glycosidic bond? A bond between sugars, right? So if you have a disaccharide, you have one glycosidic bond, right? So if you're going to break a glycosidic bond, that's just like a disaccharide breaking into two monosaccharides, so that must be hydrolysis. Okay. All right, so now let's talk about these glycosidic bonds. We need to be able to say in words how glucose, well, how any sugar molecule is attached to one another. And so we talk about it using that cis and trans, that alpha and beta anomer, and we use it by numbering the carbons. So how do we number our carbons? Can y'all remember? We find the anomeric carbon. It'll be carbon 1 if there's no other carbon outside of the ring that's attached to it. Okay, so be careful about that. So look at our first molecule here. Where's our anomeric carbon? Right there, that's our anomeric carbon. So our anomeric carbon becomes number 1 because there's no other carbon outside the chain attached to it. And then you can number 2, 3, 4, 5, 6. Okay, let's number our other ring. Where's our anomeric carbon? All the way over here. Right, how do we know it's the anomeric carbon? It's bound to 2 oxygens, and one of those oxygens is inside the ring, right? Okay, so it doesn't have any other carbon, so 1, 2, 3, 4, 5, 6. So I'm going to name this by number 1 saying if the glycosidic bond is in the trans position or in the cis position. So we're always going to compare it to this carbon up here. So is it trans or cis? This is trans, and another way to say trans is alpha. Okay, so we're going to call this alpha. And then we're going to put in parentheses the numbers for only the anomeric carbon, well, for first the anomeric carbon, then the carbon of the other ring. So start with your anomeric carbon. What's your anomeric carbon's number? 1, and then put an arrow because this is the bond that's forming between carbon 1 and carbon what? 6. Carbon 1 and carbon 6. So this is an alpha 1,6 glycosidic linkage. Okay. We all right on that? And we're going to go to the other page. All right. Now, we have to name our glycosidic bond. Then we also have to undergo hydrolysis. What is hydrolysis? Breakdown, and we're going to break water, right? Okay, so how do we find our anomeric carbon? Do it for both molecules, the one attached to the oxygen, and it's also attached to another oxygen that's outside of the chain, right? One in the chain, one outside. So let's number our carbons. For the top, 1, 2, 3, 4, 5, 6. Tell me about numbering that bottom sugar. Is the anomeric carbon carbon 1? No, it is not. It is not. This is my anomeric carbon. It's attached to another carbon that's outside of the ring. What do we call that carbon? That becomes carbon 1. So here is carbon 1. Then 2, 3, 4, 5, 6. Be careful with that. Okay, so let's name this linkage. Tell me about my red, the one that I did with the red numbers. Cis or trans? It's trans, so this and this are trans. So is that alpha or beta? Alpha, so we call this alpha. And then tell me about the carbon numbers. 1 to 2, but I'm going to tell you that's not quite enough. There's something unique about this molecule. Anybody figure it out? Something different about it. Do you notice your glycosidic bond? You have 2 anomeric carbons participating in that glycosidic bond. What we did before, everything we've done before, if I go back, do you see how we did this one? That's an anomeric carbon. It's participating in the glycosidic bond. Here's my other anomeric carbon. Is it participating? No. What do we call that? We call that a free anomeric carbon. That is a carbon that does not participate in the glycosidic bond. You need to write that down. Does not participate in glycosidic bond. So if you only have one participating in the glycosidic bond, that's the one you tell, is it alpha or is it beta? But now we have 2. Okay, we have 2 anomeric carbons, one right there and one right there. And do you see how they're both participating in the glycosidic bond? They're sharing this oxygen. So what do you think we need to add to our name? Is this cis or trans? This is cis. How do we call cis? Beta. So this is alpha beta 1,2 glycosidic bond. So this is like the 2 places where people make the most mistakes in one problem. You have an additional carbon that's attached to one of the anomeric carbons, and you have 2 anomeric carbons participating in the glycosidic bond. So this is a doozy. But if you have the hardest one in class, then makes the exam better, right? Okay, so now we've got it named. We need to draw our products. So what I want you to do first is to just draw everything that you know that's not going to change. And one thing I did want you to notice is we don't draw hydrogens anymore. Remember how when we started doing skeletal diagrams, we stopped drawing hydrogens? Same thing. So we're no longer going to put the H coming down here. We're just going to leave it off, and we're going to assume you know that there's a hydrogen there. Okay. Now, in order to have this go through, I want to move this. Okay, in order to have this go through hydrolysis, we're going to use up water. So we're going to add water and we're going to use it up. So you're going to have HOH. So when you look at that oxygen, remember how we had the R, O, and another R group? Remember that? And one of the R groups got the OH and the other got that oxygen, so it only got 1 hydrogen from water. So you're going to do exactly the same thing that we just drew, except it looks a little more complicated, but it's really not. So what I'm going to do is I'm actually going to draw my hydrogen in red. That way I can see what's happening. So this one, I'm going to arbitrarily give it the oxygen. So the one that got the oxygen, what does it get from water? just a hydrogen. And I shouldn't have drawn the stick going up, just half the stick. Okay. All right, so then I need to draw my other monosaccharide. I'm going to draw everything that's there. Okay, now, this is where that glycosidic bond was. So what goes there instead? We took a hydrogen from water, what's left? What's left? We took away our hydrogen, what's left? A hydroxyl. A hydroxyl, yep. So y'all okay on that? Okay, and I think the next one, I didn't answer part of the question on the video. Are y'all ready to move on from this one? Are you okay? Yeah? All right. Okay, so here, 6.38. I did this one in the video, but I neglected to answer part B. Look at that, your teacher didn't answer all parts of the entire question. Okay, so, right, we had to combine two monomers and make a disaccharide. And so we made our disaccharide, we drew our structure, it is lactulose. Is it a reducing or a non-reducing sugar? How did we define a reducing sugar? Are we skipping part B? Was there a part B on there too? Oh, okay, yeah, I'm gonna, let's answer this one and then I'll go back and do B. Sorry about that. So is this a reducing sugar or a non-reducing sugar? How do we define that? Remember, for a reducing sugar, if it's a reducing sugar, what? You look at the anomeric carbon. A-N-A-M-E-R-I-C? I don't know. Anomeric carbon, y'all know what I'm talking about. The anomeric carbon. So how do we know if it's reducing? If it is free. What does free mean? It's a free anomeric carbon, that's right. But what does free mean? It is not participating in glycosidic bond. Good. Oh yeah, I can't spell either at all. I really, really can't. It's okay. So in my new molecule, here's an anomeric carbon and here's an anomeric carbon. Do we have a free anomeric carbon? Yes, this one right here is free. So this is a reducing sugar. Good. I'm sorry I missed that on the video. And now I'm going to go back and get part B. Speak of my mistakes, right? Now let's go back and get part B. All right, so for this one, for part B, we have to go through hydrolysis again, right? So let's name it. We have to find our anomeric carbon. So we have an anomeric carbon here. And that becomes carbon 1. Where's my anomeric carbon on the second ring? Is it the one participating in the glycosidic bond? No, it's not. It's right here because it's bonded with the oxygen, 2 oxygens, and one of those oxygens is in the ring. Good. Okay, so if that's our anomeric carbon, we're going to go 1, 2, 3, 4. So tell me, what kind of a linkage is this? It's a what? Beta 1,4. And how did you know beta? Because this is top, so this is cis, and cis is beta. Okay, now we have to draw our products. So draw exactly what you had before. Okay, that looks good. And then we had an oxygen over here, but I'll just leave that off for now. Okay, let's draw our other one, plus oxygen. So everything's exactly the same except for the stuff that participated in the glycosidic bond. So now, what are we going to do about that? On our first carbon molecule, or our first ring molecule, we know we have HOH, right? H2O. HOH. So one of these carbons is going to get the oxygen from the glycosidic bond. Let's give it to the first one. So what else does it need? Does it need the H or does it need the OH? It needs the H. Okay, and our second, now be careful, should it go up or down? It should go down. OH. So tell me about monomers. Tell me about monosaccharides. Are they reducing or non-reducing? They're all reducing, right? They all have free anomeric carbons, all of them. In a disaccharide, you have to look. You have to try to figure it out. But in a monosaccharide, they're all reducing, right? So that's a good trick to know. All right, so, oh, and here's my other error from the video. I was reading one and answering the others on the other one on the video. I don't know if anybody else noticed this, my mistake. When I was trying to do 6.40, but I was reading 6.39. So let's go through each of these individually. If it's an ordinary table sugar, what kind of disaccharide is that? It is sucrose. If we find it in milk and milk products, that is lactose, right? You've heard people who are lactose intolerant, right? Y'all know the milk that you get at the grocery store? And next to the regular milk, they have, what is it called? Like lactate or something like that, right? For people who are lactose intolerant. Does that have lactose in it? It started out as regular milk, and all they do is add an extra enzyme that can break down lactose. And so that's all it is. It's regular milk with an enzyme that breaks down lactose. So the person consuming its body doesn't have to do it, right? That's why it tastes kind of different, because each of the different sugars have a different conformation, and so they taste a little different. All right, also called malt sugar. Maltose. right? Easy, maltose. Hydrolysis, so this means it must be a disaccharide, gives galactose and glucose. Galactose and glucose together make lactose. Okay, so now let's do these. A non-reducing sugar. So what's a non-reducing sugar? One that participates in a glycosidic bond with both carbons, like this one right here, right? This is both anomeric carbons participating in the glycosidic bond. So what kind of sugar is that? That would be sucrose. So A is sucrose. Composed of 2 glucose units. Any takers? This one is maltose. Okay, also called milk sugar. Lactose. Yeah. And hydrolysis of this one gives glucose and fructose. That is sucrose. Good. So sorry about that. I don't know how I did that. Okay. So the last thing in this section talks about regular sugars versus artificial sugars. So when we talk about how intensely sweet something is, we compare everything to sucrose, right? Sucrose is our table sugar, and so we just arbitrarily set it at 100. So anything that is sweeter than sucrose, sweeter than table sugar, has a higher value, right? So fructose is sweeter. It has a higher value. What do you see in a lot of your food ingredients? That has the word fructose in it. High fructose corn syrup. So why? Why do they put fructose in there instead of sucrose, right? Well, the answer is that it only takes half as much fructose as it does sucrose. So what they can do is, if I want to produce so many of whatever my product is, I don't have to buy as much sugar if I use fructose as if I use sucrose. So it's a way for food manufacturers to save money. And so that's why we see it on so many things, so many things. All right, and then we come down here and we see these artificial sweeteners. So our artificial sweeteners, look at the sweetness level. That's insanely high, right? So how is it, I know you've gone down the baking aisle, right? And you see the big bags of like stevia or Splenda or whatever it is, right? And they say, the label says on there, perfect for baking, matches sugar spoonful to spoonful, right? Have you seen that? So what they're saying is that what you're buying, if you take 1 spoonful of it, it will taste just as sweet as 1 spoonful of sugar. Tell me, how many molecules of sucrose versus how many molecules of sucralose are there, right? You're going to have a lot of sucrose, and really you're not going to need much sucralose or Splenda, right? Because it's got 60,000 units of sweetness. So when you buy that big old bag of Splenda, you're only buying a little bit of Splenda. Do you know what else you're buying? Filler. So that it measures the same. So that when you pull out your recipe book and it calls for 2 teaspoons of sugar, you just get 2 teaspoons of your artificial sweetener and it works out, right? So that's how those companies do that, even though their sweetness levels are drastically higher than normal sugar. So you're buying a lot of filler. And the higher the percentage is, right, the more filler there is. So this one, which I've never even heard that name before, but that's okay, is only double like whatever table sugar is. All right, so if you have one sweetener packet of Splenda, sweet and low or equal, which one has the same sweetness as 2 tablespoons of sugar? Oh, no, I'm sorry. If one sweetener packet of each of these has the same sweetness as 2 tablespoons of sugar, which of the packets contains the smallest amount of sweetener? So which one has the least amount of sweetener and the most amount of filler? Out of Splenda, sweet and low, or equal? So we want to know most filler, least sweetener. This is artificial, but A-R-T-I-F-I-C-A, artificial. So whatever one has the least is going to have the highest sweetness taste, right? Because you're not going to need very much of it in order to taste like a tablespoon of sugar or a teaspoon of sugar, whatever it is in there, right? So it would be sucralose or Splenda. Which one would have the most would be equal. So this one has the least amount of sweetener. This one has the most from our list. They gave us 3, right? Splenda, sweet and low, and equal. Splenda, sweet and low, and equal. So this has the most amount of artificial sweetener. Make sense? Okay, that's it for today. Remember, when y'all come on Thursday, you need those extra sheets that I showed you on Moodle. Any questions? All right, y'all have a great afternoon. Anybody on the chat have any questions? Is it actually healthier? Well, it depends on what you mean by healthier. Everything that you ingest is going to have an effect on your body, absolutely. So reducing the amount of sugar in your diet is probably a very good thing. So everything in moderation, but it's almost better to just get used to eating things that are not as sweet versus actually ingesting lots of artificial sweetener, because your body can metabolize them into things, right? So if I wanted less sugar but the same taste, yeah, you can do like half and half too, if you wanted to do like, because some people say the artificial sweeteners don't taste as good, but yeah, if you want the same taste but less sugar, if you ingest the artificial sweeteners, they do not increase your blood sugar levels, so your cells don't take that in as glucose, and so then you end up not storing it as fat. So it's a good thing in terms of that. Does that answer your question, Jason? All right, good. Okay. Well, have a good afternoon, and if y'all need anything, shoot me an email. Oh, what do I know about A2 milk? I don't know about A2 milk. What is A2 milk? Y'all heard of that? A2 milk? Never heard of that. Do you know what it is, Jason? Kind of. I don't know. I'd have to, you have to drink it. I don't know. If you send me an email, we can kind of try and figure it out together. But I've not heard of it, so I don't know. All right, so, but not like, I don't know. Send me an email, because I got a few people who have questions, but send me an email and I can look it up for you. All right. Okay, I'll see you guys on chat on Thursday. Ooh. I had to end. There we go. Okay. I thought I ended.